This is not an ordinary acid. It is a superacid, so powerful that sulfuric acid is almost harmless in comparison. To understand its strength, imagine something 20 quintillion times more corrosive than pure sulfuric acid. That number is so large it almost stops making sense. When this substance comes into contact with matter, it doesn't react, it erases. Glass doesn't crack, it vanishes. Gold doesn't corrode, it dissolves instantly. Even organic material cannot survive even a fraction of a second. By every rule of chemistry we know, this should not be containable. No material on Earth should survive direct contact with it. And yet, this same substance is safely stored inside a simple plastic bottle, the same kind of material used to hold soda. So the question becomes, how is that even possible? To understand this contradiction, we first need to look at what this acid actually does at a molecular level.
Every chemical in science starts with one assumption. Glass will contain it. Stable, transparent, reliable. But to this acid, glass is not protection. At the atomic level, the acid attacks the silicon-oxygen bonds. Using a process called protonation, it forces the structure apart from within. What looks solid stops being solid. So scientists turn to something stronger. Metals. Materials built to survive extreme conditions. But metals have a different weakness. They rely on electrons to stay stable. This acid doesn't just react, it steals electrons, pulling the metal apart from within. The bonds weaken, the structure fails, and the metal begins to break down.
At this point, glass has failed. Metal has failed. So what could possibly survive this acid? The answer is plastic, but not ordinary plastic. This material is called polytetrafluoroethylene, or PTFE. Unlike glass or metal, PTFE is built differently. Its carbon atoms are surrounded by fluorine atoms, and together they form one of the strongest bonds in organic chemistry, the carbon-fluorine bond. Breaking this bond requires enormous amounts of energy, more than this acid can easily provide. But the real secret is not just strength. The fluorine atoms surround the entire structure, creating a protective electronic shield. So when the acid reaches the surface, there are no weak points to attack, no accessible electrons, no easy way inside. For the first time, the reaction stops. And that is why one of the strongest acids ever created can be stored inside plastic.
But this immediately raises a new question. It's not just why it works, but how something like this can even be built. Because not all plastic containers are the same. The bottles used to store this acid are not ordinary. They are engineered with extreme precision, made from highly purified fluoropolymers, processed under strict conditions to remove any structural weaknesses. At this scale, even a microscopic impurity can become a failure point. A single defect in the material could allow the acid to break through. So the manufacturing process is not just production, it is control at the molecular level. And because of this complexity, these containers are far more expensive and far more specialized than everyday plastic bottles. But the purpose of all this effort is not just containment. By controlling this extreme chemical, scientists gain access to reactions that would otherwise be impossible. This includes the creation of high-octane fuels and modern pharmaceutical compounds that rely on precise chemical pathways. In more advanced research, the interaction between superacids and fluoropolymers is even being studied for next-generation battery systems as technology moves towards 2026 and beyond.
But perhaps the most important idea is this. The most aggressive liquid in chemistry is not useful because it is destructive. It is useful because it can be controlled, and it is only controlled because it is contained by one of the most inert materials ever created.